In previous lecture, we showed that the Newtonian Sobolev class of functions on a compact subinterval of Rn coincide with absolutely continuous functions there without the need to change the representative or anything. Analogously, you can talk about N1P space, except that you will require that other than being in AC, the derivative, the pointwise derivative, also belong to LP of that interval rather than just L1. With L1, that L1 integrability of derivative is part of the theorem of Lebesgue about absolute continuity, or rather characterization of absolutely continuous functions as those that arise as antiderivatives of L1 functions. In this one, we want to talk about what happens when we look at all of R1, which is non-compact and is built up of unions of compact intervals. So, not surprisingly, again, we will see the connection to AC functions plus fixing for integrability of the function and the derivative. Let me first motivate with this example that the constant function 1 is not in N11 for the technical reason. It's not really a deep reason, so this does deserve to be called a smooth function, but per se, technically it's not in this class because it does not belong to L1. It's just not integrable. Its derivative, though, which is just 0, and also it's an upper gradient, is in L1 nevertheless. So I'm going to call this space R1 equate with the standard metric and the Lebesgue one measure, my matrix measure space X. Such examples actually have motivated a quite important class of functions called Dirichlet class. So the Dirichlet class of functions, say on a metric measure space, will be those functions, real valued in our case, such that U is measurable. We don't require any integrability, even locally, but its upper gradient is integrable, and it has an upper gradient, which is, remember, a Borel function satisfying this upper gradient inequality along every rectifiable curve. And it has an upper gradient rho from, that is LP integrable. So, and this does include constant functions because rho is 0 and we don't require any integrability of the function itself. So this is quite interesting class of functions. The idea behind that, and we will in future see that, is that from only integrability of, integrability of derivative, whether it be in the Sobolev, classical Sobolev space in open set sub-Euclidean space, whether it be the Newtonian Sobolev function, in either sense of Sobolev classes, just from integrability of derivative, we do get, through, say, Poincare inequality, in very reasonable spaces where Poincare inequality does hold, only from integrability of derivative, we get, at least locally, integrability of function itself. So in a sense, even when you go back to classical Sobolev theory of W1P functions, the integrability of the function is not as significant a factor as that of its derivative. It's the integrability of the derivative, the tameness of the derivative of a function, that pretty much dictates how smooth and nicely behaved the function is. And hopefully in the example that I will do on R1, you will see some elements of this interplay. So let me prove to you this theorem that if a function u is in n11 of R1, we can do similar things with n1p, but for simplicity, I'm going to stick to this. So if u is a function here, I'm going to prove that then u is in AC of any compact subinterval. So for any a, b compactly contained in R1, we can call this locally AC loc. Remember, AC is defined only on compact interval. On non-compact interval, you can still define them by straightforward modifications, but we don't really need that language and terminology. So this is as clear as it can get. So on every compact subinterval, it is AC. Moreover, u itself, okay, wait a second. So I'm gonna actually just assume that its upper gradient belongs to L1. So we know that this is AC function, so u prime in classical sense, pointwise sense, we know that if you have a AC function on a compact interval, the derivative exists almost everywhere. Is well defined on all of R1 because derivative is a locally defined object, and if you have this for every compact interval, you get that. And this u prime, and moreover, this limit of ux as x goes to infinity exists. Similarly, we can say similarly for x goes to negative infinity, the limit exists, but it could be a different one. I must add that and is a finite number, so exists as a finite value. It's not infinity. So just from the fact that the upper gradient is in L1, we get that this limit exists when you go to either infinity. Yeah, so this basically is close to characterizing to saying that you are in N11 of all of R, basically if you are in a C locally in R. If you change to N1P space, so we have this derivative existing, we have to assume that, it follows that this U prime is in LP rather than L1. The converse direction, we can also cook something up. I didn't want to get into that. The proofs are straightforward, but kind of technical. You have to follow the definitions exactly. For reverse direction, basically, you start with a C function, and you assume that U prime is in the right LP class. You basically need to prove that rho equaling absolute value of U prime is basically the upper grading. You have to be careful by the fact that this is not necessarily Borel we need Borel in definition of upper gradient, but you can change this measurable function to a Borel function only adjusting the values on a set of measures 0. We've seen that before. So I'm just telling this so that you can probably work out some lemmas on your own in the reverse direction. And let me add this remark, as we will see in the proof, that if U is actually in N11 of R1, this is our L1, then the limits that we said exist are both 0. Because if they are not 0, remember U is continuous, and if it is not 0, you will have something like this at infinity, and then U cannot belong to any LP class, in L1 definitely, which violates that U itself belongs to L1. But since here we only assume that U is in D11, this is no violation that the limit be something other than 0. Okay, so let's go ahead with proof of this lemma. We don't need to prove that this U prime is well defined. This is simply because the function is in AC. This part that it does belong to AC, well, let's see that. So if Y is a Borel subset of, so this fact that if you take a Borel subset of a metric measure space, then if you fix a function that is in N1P of X, then restriction of U to Y, as it is, without any need for adjustments, will belong to N1P of Y. Because the upper gradient restricted to Y is still a Borel function on Y, and it still acts as an upper gradient. Integrability just goes through and everything. So this is a general observation. If we apply it in our case, thus, if U is in D11 of R1, then U belongs to D11 of any compact interval. Okay. So this proof similarly works, of course, for D1P. It's all about the upper gradient. But U of X minus U of A is bounded by integral over the line segment, over the canonical path that connects A to X of the upper gradient of function U on S, where rho is the upper gradient of U, and this is like on all of our one upper gradient. And by assumption of being in D11, this integral rho of A to X is bounded for any X, even if you are outside this compact interval AB. This shows that U of X let's say this is less than m for some m. This shows that u of x, absolute value, is less than u of a plus m. So u is bounded on a, b. Now u is bounded on a, b. Rho restricted to a, b is an upper gradient, and it is also in L1 gradient of u restricted to a, b. From these two facts, it follows that u is in n11 function over ab. So this is the thing I mentioned about having derivative in integrable implies that the function itself is locally integrable, and this has happened. So we started with d11 of all of R1, but when we localize, we look at compact subintervals, it upgrades to being actually in n11. And from previous lecture, we see that, or actually we have almost repeated the previous theorem from this inequality. Basically, you apply it to partitions and you get absolute continuous. So u belongs to absolutely continuous functions on the compact interval ab. As I mentioned, from this we see that u prime exists almost everywhere on ab. Maybe let's drop the endpoint. And because ab is arbitrary, u prime exists almost everywhere on all of R1. Okay, now the existence of the limit thing. For the existence of limit, notice that if, let's say, x and y are positive values, then u of y minus u of x is less than or equal to integrating the upper gradient, again on the path which connects x to y, ds. Which is just integrating this function against the Lebesgue measure from interval x to y. Okay, where rho is the upper gradient of u, where rho is in L1 of all of R1 is an upper gradient of u. Okay, now if you have an L1 function on all of R1, if you take this x really large, y is even larger, this integral actually has to go to 0. The integral cannot accumulate at the end, at the tail. So here is the claim. So for every epsilon positive, there exists some n such that if x is bigger than n and y is anything bigger than x, then integral of rho is non-negative, remember, dl1 of t from x to y will be less than epsilon. This shows that say you take j belonging to n is a Cauchy sequence, right? Because if you give me an epsilon positive, I actually take this n, and for j bigger than that n, for j and j prime both bigger than that n, we will have their difference here less than epsilon. So because this is a Cauchy sequence of real values, so it has a limit, say alpha, which is a real number and not infinity. And look, because there was nothing about picking this particular sequence of j. Any sequence of xj's that go to infinity that you pick, you will have the same assertion. And by comparing different sequences to each other, again by this inequality, you can see that this limit is independent of what sequence you take. So in fact, limit of ux as x goes to positive infinity is equal to this alpha. Again, for negative infinity direction, pretty much the same argument works. But remember that the positive and negative limits do not have to agree. There's no way we can compare the two ends. And this completes the proof. And the proof of remark again, I just gave you, because if limit is other than 0, the function u cannot be integrable. Okay, so some useful things come out of this. So we saw that if u has an integrable upper gradient on all of R1, then a limit of ux at the two ends exists, which is quite nice. So because we start off with Sobolev functions. Okay, this is also true with the classical Sobolev functions. So we can have W11 will force this limit to be 0 because this is equal to N11. We've mentioned that before. And if you go without the integrability assumptions on the function, which is denoted often by this space L1. So this is the classical Sobolev functions, except that you don't require integrability of the function itself. I think we can get that the limit exists, but could be other than 0 part. And that these are locally absolutely continuous. This kind of questions actually deserve attention. There is a paper by Perka Koskela and Gwen. I think, yep. Where they look at the question of whether if you have a graph, say k arrays, so every vertex has 3 descendants in our case, and so on, then you can actually put weights on these edges so that the farther down you go, the shorter the edges are, so that you can equip it with a nice distance, which makes the kind of the distance to the whole end computable. And then you put also a measure on that, and then you can ask, so the question they answered was, under what conditions do we have that a function in D1P or in N1P has a well-defined limit along the at infinities, along these infinite path. And it's pretty recent paper, so what I'm trying to say is that even with the rather beginner examples, you can still ask interesting questions about Sobolev, Newtonian Sobolev functions, and start your own investigation. Hope this gives extra motivation for you to get serious about this particular topic. Thanks a lot for watching. I know this wasn't too polished, but I also liked how it worked out finally. So I'll not re-record this, and hopefully that's okay.